in exercise 3b, we will apply XGBoost. So first we install and import the XGBoost library. Then we will split our training data into X and Y sets, and the same we do for the test data. Next, we have to convert these data matrices into a certain form, which is the D matrix. This is necessary, this is a requirement of XGBoost. First I have to run this, of course, and then I can run this cell. Now you see that the inputs are the train X and train Y, and here for the test matrix they are test X and test Y. So now we have to set the parameters for the XGBoost model. So which booster do we want to use? Should it be a tree booster or linear model? Then the objective function, and then all these other hyperparameters, some of which you may know, like max depth or gamma or eta is our alpha value from the lecture. So these are basically just the default values, which we could tune. We could do hyperparameter tuning, but tuning all these parameters is an art of itself, and it would take a lot of time to explain this, much more than we have for the exercises. So I don't know if I will make an extra video about hyperparameter tuning, but for now, let's just stick with the defaults. So now we can build our regression model. So we use XGBoost, then set our parameters, our data, which is our training data matrix, the number of rounds we want to train, and then where both equals 1, it just says we want to have a look at the training process. And we see here how the train RMSE is declining, which could also indicate some overfitting, because it is always declining, and it yeah, so at this point, maybe after 100 rounds, this could be overfitting, which means we maybe the hyperparameters are not set correctly. We could adjust some of the parameters, for example gamma, to get better predictions, or to combat, to counter overfitting. Let's have a look at the predictions. So we predict again using our model, the test data, and set the type to class. Not class, sorry, still regression. And now we can calculate our RMSE, and we see that it's 3.59. So this is now just the RMSE from this, so the out of sample RMSE for this untrained, or not untrained, but untuned XGBoost model. So if, let's say, we want to use a little more regularization, then we could tune, for example, gamma. So here I set gamma to 50. We'll train this, and you see that after a certain point, the training RMSE doesn't decline anymore. And if I now calculate the predictions and the out-of-sample RMSE, we see that now the out-of-sample RMSE is smaller than before, so our regularization actually improved the generalization of the model. Now we can use this also for classification. So here I do this XY splitting for train and test set using our classification training and test set. And then I convert these into the D-matrix format. Now here again the default parameters. And now I can build the model just as before. Maybe I have to say that for the parameters now, we have to specify a different loss function. So the objective before was a squared error, and now our objective is a multi-class softmax. So we need to specify this so the algorithm uses the appropriate loss and the fit is actually good. So let's build the model, which is also again indicating overfitting. And then we can produce our predictions, and the classification error, which is out of sample, is actually quite nice. So this is even better if we think back, even better than the optimized random forest that we had, which was, I guess it was 0.46. So this is now slightly better, although we did not use great hyperparameter tuning for this. Now, to see the variable importance, we can just use the built-in XGBoost importance and then plot this. And here we see the importances of the variables. We could also print the matrix itself so we could see the exact values, but I think that's not necessary right now. Of course, we can also use cross-validation using xgb.cv, then setting the number of folds. So this would be a 10-fold cross-validation. So this also might take a few seconds, although the XGBoost algorithm is very efficient. And here we can see, for example, for all the for the 10-fold cross-validation, the mean train error and test error. So it's the mean over the 10 cross validations. So the 10 samples, and we see that here for example, the train error, the mean train error is declining steadily, and monotonously, which is not the case for the test error, which is declining and then increasing again, and here it's locally getting smaller again and then increasing again. So it's not like a stable reduction in test error. So we could also use some regularization here, or maybe also early stopping, which I guess we will discuss in a later class, which is also a method that will interrupt the training at a point where the out of sample error is very low.